Welcome to the course on principles of vibration control. Today we will enter a new regime which is active vibration control. So, we will talk about how we can use an array of sensors and actuators and develop some kind of a feedback and feed forward systems, and we can control the vibration with the help of such a system. Just a bit of recapitulation, if you remember that we have talked about several vibration control strategies in the beginning of this course, and the first one in that was reduction of vibration at the source itself. So, which we said that this is the most inexpensive way of controlling the vibration. Then we have talked about that vibration isolation. So, development of isolation systems or inserting a resilient systems, so that the vibration from the ambience cannot propagate. Then thirdly, we have talked about system modification, where we have said that by retrofitting or changing the stiffness, mass or damping, you can actually control the vibration. Now, these were generally passive techniques, whereas towards the end we have talked about two more techniques. One is a semi passive technique, and that is energy harvesting. I am going to talk about a little bit more details on this technique towards the very end of the course again, that is semi passive, and finally the active one, in which today we will talk about the active vibration control. We simply call it AVC, using different types of classical, modern and distributed control technology. So, this is what we would like to discuss in this phase of the course. So, today I will first give you a brief introduction to active vibration control. We will talk about some of the traditional applications of these concepts. We will also talk about the problems with active vibration control, particularly the problem which is known as spillover, and we will introduce basic control strategies. So, fundamentally the active vibration control can be thought of in this manner, that suppose you have an incoming vibration. So, this is the incoming vibration signal, and then if you are generating a cancellation signal, which is just, as you can see here, that it is just opposite in phase. So, that means in this part it is like this, whereas in this part it is just the other way. So, this is a cancellation signal. Now, you imagine what will happen is that every time it will happen in this manner. Okay. So, each one of them will be cancelled by the other, and as a result you will get a zero net effect. In order to do that, that means you have to know what is the nature of this incoming vibration. For example, you have to know that what is the time period or what is the frequency of the system, because the cancellation signal frequency has to match with it. You have to also know what is the magnitude, and then the cancellation magnitude has to be comparable even if it is not exactly matching. So, you have to know the nature of the incoming vibration, and then you have to decide on the cancellation signal. That is the strategy of active vibration control. Now, how do I know the nature of the incoming vibration? With the help of sensors. So, here we will use various types of sensors, for example, accelerometer, which is very regularly used, which senses the acceleration, and also something which senses the velocity, like piezoelectric systems, or position, So, we need this type of various types of sensors of these things in order to determine the nature of the incoming vibration. How do I generate a kind of a signal, a cancellation signal which is almost equal in magnitude to the incoming vibration? For that I will need actuators. So, that is where you will need the actuators. There are various actuators again, like we will say smart actuators is one of these categories, that is based on smart materials. Then of course, there are electro-hydraulic actuator, there are electromagnetic actuators, there are electro-pneumatic actuators, there is a long list of actuators. So, with that let us see how this motivation of applying this concept would come. Now, this was initially very much important for space structure, where the traditional passive vibration control strategy was not welcome because there was a high weight penalty in such a system. So, this kind of isolation systems that can dynamically react to incoming vibrations rather than passively reducing their effect was actually was a very welcome idea. Also, many other equipment, not only for space application, like in car engine or in an altitude control assembly in a spacecraft, in many such things we generate oscillatory forces which can propagate in the supporting structure. For example, I told you that in any engine, because of the nature of internal combustion engine, there will be always this oscillatory force generation. So, in such cases a vibration isolation is necessary, and using active vibration control systems this can be achieved beautifully. You can get a much better what we call an active suspension system. You can see some of the examples like Bose's active suspension system. So, this is the main motivation of the active vibration control. It was first introduced in a group of space structures generally known as large space structures. For example, the International Space Station, this space station itself, as you can see, which is the man-made biggest structure in space, and they are actually this kind of because it is very flexible. So, in this kind of a system ABC is needed. The fundamental modal frequency of this International Space Structure is about 8 Hz, and its structural damping is phenomenally low, only 0.358%. So, this is a classic case where you have a flexible body, 8 Hz fundamental frequency is very flexible, and once the vibration starts it would not stop because the structural damping is very low. It has a very low inherent damping. So, when there is an absence of air because there is no resistance, so this poor damping can easily result in actually fatigue failure in the system. Now, if you try to use passive dampers, there will be large weight penalty. Also, there are issues like in such a low frequency, not many passive dampers will be able to work properly. So, active vibration control is the only feasible solution in such cases. There are also some classical problems which we call as control structure interaction or CSI, and that is particularly useful for any flexible body, not necessarily for International Space Station. So, in one of the example is where for example, you need a very high pointing accuracy like in Hubble telescope. During maneuvering of Hubble telescope, if you excite inadvertently the structural modes of vibration during any such maneuvering motion, as you can see the Hubble telescope here with so many complex parts in it, a small 10 microradian of filtering motion will be equivalent to a 50 meter shift in the field of view, and that for an imager at a distance of only 500 kilometer. So, you can imagine how much will be the huge change in terms of its field of view, because only within 500 kilometer itself there will be a shift of 50 meter. So, if you talk about millions of kilometers, how much of shifting it would happen. So, naturally you need a very high pointing accuracy of these flexible structures, even though it would be subjected to vibration. So, active control of vibration using an array of actuators and sensors again is the only feasible solution in such cases. There are many such examples. There is one traditional application of AVC that I want to tell you. It can be used in applications like helicopter rotor blade. So, this is typically one of the kind of a cantilever beam which represents a helicopter rotor blade. Now, in this system you can use control systems integrated with electromagnetic, electrohydraulic or pneumatic actuators. And for example, you can see here that you can have sensors which can sense these signals, and then all these sense signals come through operational amplifiers. Then there is a power amplifier here, and then there is an actuator here. This actuator here right now is an electromagnetic actuator, but you can also have electrohydraulic or pneumatic actuators of very similar type. So, depending on the sensed signal, the force is actually given to the system such that the vibration can be controlled in the system. So, this is a traditional application for helicopter wings. There is another popular one, it is based on a control of magnetic levitation, and that is, for example, in this particular case, as you can see that there is a spring here and a spring mass damper system is a traditional system, and this is a plate here, and the plate has a permanent magnet in it. Okay. So, the whole system is resting on the spring damper system, and it is a single degree of freedom system which has a permanent magnet in the top. Now, this base I can subject it to some kind of a base excitation problem, which is very typical of this kind of vibration isolation systems. And whenever this vibration takes place, I can control the current in the electromagnet, so that these, suppose this is a north and the south polarity, so that I can generate a north south here, so that I do not allow the magnetic force will stop these to move beyond a certain point, because the north poles will start to repel each other. So, similarly, once it is going down, in that case once again you convert these to south and north and you attract it, so that it does not go down also. So, both for upward as well as for downward movement, you control this movement with the help of electromagnet, the magnetic field of the electromagnet. So, this is a very traditional application of the system. You can, instead of using electromagnets today, you can use things like PZT based actuators, which has a very large bandwidth and is also much faster and less noisy than this kind of a system. But this is a typical of a smart suspension system. This is the way it actually behaves. Now, what are the problems with this active vibration control system? Since active control system essentially adds energy to the vibrating system, we have seen. Now, what is the disadvantage of this active vibration control? Well, active vibration control has certain basic problems. For example, it adds energy to the vibrating system. So, it may also create instability because it is adding energy to the system. Consider that you have the active vibration system which is adding which is working on a vibrating system which is having a motion like this, and it is supposed to, so that means at this moment the structure is going up. So, it is supposed to add a downward force to cancel this motion. Now, if by chance instead of this downward force, if the phase gets shift and it adds an upward force, then this amplitude will become double. So, instead of controlling the vibration, we are going to have higher and higher level of vibration. So, that is what will create actually instability in the system. So, this happens generally if there is a erroneous sensor or there is a phase lag in terms of actuation. That means, actuation is working slowly instead of quickly actuating the system, it is working with a delay. So, then this kind of problem would happen. The other problem with AVC is that these systems are generally quite expensive, because you now need a set of sensors, you need microprocessors, data acquisition systems along with the sensors, actuators, signal conditioners and power amplifiers. So, it is quite expensive system. And also active systems work efficiently within a finite frequency band. Say for example, you have a particular frequency range, omega with respect to suppose the transfer function, if we plot and it is like this, and you have designed your active controller for this region in order to take care of the particular resonance close to this peak frequency. But then what happens is that in the regions where you have not designed it, this path may get modified. That means, you will start to get a new peak here, and that means pumping, this is also is known as an water bed effect. That means, pumping energy to the other places where it is not desired. So, this may create a severe problem which is also known as spillover problem. In fact, this is what one can identify to the biggest problem of AVC, that instead of controlling the vibration, the spillover generates a new trouble into the system. This many a times happens because vibrating systems are essentially flexible in nature, and they are generally modeled as continuous systems. Now, continuous systems has countably infinite number of natural frequencies in them, but we are not modeling a system against infinite number of natural frequencies, but only for finite number of frequencies or for a range of a frequency. So, this actuation and sensing that we have traditionally, they are then pointed in nature and they work for a finite number of actuators, and that is why they could not control all the vibrating modes of an infinite dimensional continuous system. And the trouble is that the unmodeled modes could always get excited by this finite dimensional actuation system. Hence, even though the vibration could be controlled in the desired bandwidth, the actuation energy may spill over to the unmodeled mode, causing severe resonance. This problem, however, there is a technique to resolve it which is known as distributed sensing and actuation based on smart materials, but it is quite difficult to implement. So, spillover is one of the biggest problem of active vibration control. The basic control structures that are used for AVC are single input, single output, that is also we call it as SISO system, a state space based multiple input and multiple output, we also call them as MIMO controller, and finally the distributed vibration control. So, there are three different control strategies that we can use in terms of controlling the vibration. Now, first let us talk about the single input single output control or the SISO control. So, if you have a reference signal, for example, you may or may not have, if it is just a vibration problem of something like a cantilever beam which is vibrating and you want to drop that vibration down, that is one type of a problem. But in another group of problems, instead of having this, you may have a link actually, and you may have a flexible arm, and where the job of the flexible arm maybe in an assembly process is to rotate the whole system from between two positions. Now, this is the rigid body movement, this is the reference signal that you are giving to the system. The reason of applying an active vibration control in this system is that due to flexibility while movement it can start to vibrate. So, it may give you this kind of various vibrating modes. So, that means you will lose the pointing accuracy corresponding to various types of vibrations. So, that is where the reference signal is to be strictly followed and the active vibration control signal has to work. Now, in the single input single output system, the GS here is actually the plant, that means the transfer function of a single degree of freedom system. What can be a typical transfer function of a single degree of freedom system? Let us think of it. Suppose we have something like this kind of a structure, that a spring and a damper and a mass m. So, the mass m is actually having a response here x, and when it is subjected to some kind of a harmonic excitations, as we have done earlier as f e raised to the power j omega t. So, we know that the equation of motion of such a system, we have discussed about it earlier, is mx double dot plus cx dot plus kx equals to f e raised to the power j omega t. In the frequency domain representation, this itself will take the shape of s square m plus s c plus k x s equals to f s or m per s. So, in this case, the transfer function, that is the output to the input relationship, will be 1 over s square m plus s c plus k, right. So, if I write it very nicely here, the transfer function will be 1 over s square m plus s c plus k. That is what is my G s in this particular case. You may notice that in this particular case, the G s is a second order transfer function. So, that is what is the transfer function corresponding to the plant. Now, we are applying sensors which is going to sense the displacement of the system, for example, and then the sensor may have its own dynamics, that is H s, and we are feeding it back. So, this is a summing junction. The error between the response reference signal and this sensed one is called the E s. Then we apply a controller. So, this is the controller in a single degree of freedom system, and this controller then tunes the signal and feeds it into G s, so that it actually gets properly actuated and it can follow this reference signal. If the reference signal is 0, we call it as a regulator problem. That means you are just controlling the vibration and bringing it back to the neutral state. If it is non-zero, then it becomes something like a guidance problem, in which there is a reference signal and the importance is the vibration is to be rejected and the reference signal is to be followed. So, that is the CISO control of the system. Now, whatever we do in the CISO system can be extended to a multi degree of freedom coupled systems. So, that means you consider this kind of systems, that you have one mass m 1 k 1, you have another mass lumping m 2 k 2, you have another one m 3 k 3. I am just neglecting the damping right now. This part is frictionless, let us say. So, this is a multi degree of freedom system. So, that means instead of getting one single equation of mx double dot plus cx dot plus kx equals to something, you are going to get a matrix equation here. So, you are going to get a matrix equation of motion in the time domain. This type, so that means our equation now will be something like m, capital M, which means it is a matrix, and then the vector form mx double dot plus, if there is some damping, I have not shown any damping in this model, if it is there, cx dot plus kx equals to ft. So, that is our matrix equation of motion. Now, this kind of systems can be easily, as this is a second order system, this is a second order ODE in a matrix form, you can actually break it into first order ODE, and then what you are going to get is actually a state space form of the system. And in that form, when you will be controlling it, then this is known as a multiple input multiple output control. We will talk about it in one of the next lectures with little more details. The last type of control strategy is actually distributed control strategy. In this case, we are considering the governing equation of motion in the form of partial differential equation itself. So, instead of considering the ODE, we are going to consider the PDE. So, then the error due to modal truncation will be avoided, and usually with smart material based distributed actuation system is typically suitable for applying this kind of a distributed controller. So, it is generally very difficult to implement in real time, but what you can do, you can develop a discretely distributed controller which can have a limited applicability. So, thus there are these three types of control strategies which we can adopt: a very simplified one, that is SISO, slightly more complicated, that is MIMO, and more complicated, that is distributed controller. We will first see that how for SISO we are going to use this strategy for active vibration control, then we will see for other type of control strategies. So, first we are going to concentrate on the feedback control of a SISO system for vibration control. So, here is this control structure again. You have the vibrating system, you have a control input here. So, that means the controller is actually integrated here. So, if you remember that you have this Kc there and there is this plant Gs, all of them, let us say that they are integrated in this vibrating system, and the feedback gain is here. If it is unity, then directly you are getting the sensed output and you are exciting the structure in a closed loop manner. So, that is what is the closed loop control of a SISO system. Usually for sensing, I told you that accelerometers are used, and for actuation you can use electromagnetic, electrohydraulic or piezoelectric actuators. Now, what will be the closed loop transfer function of such a system? If you look at any basic control book, a closed loop control of a classical control, then you will be able to get this. Let us try to get the same system. So, as you can see here that initially we start with RS, okay, and then the difference between RS and the sensed output, which is Cs here, and once it passes through this transfer function, it becomes HSCS. So, my ES, the error function, is actually RS minus CS HS, and this error function I am applying, passing it through the controller. So, it becomes KCES. So, that means it becomes KCR minus CH. All the S's are implicit, so I am just taking it out. Finally, it is going through GS. So, then it becomes GKCE. That means it becomes GKCR minus CH. But what is my GKCE? This is nothing but the CS itself. So, actually this GKCE can be written as C equals to GKCR minus CH, and now all we need to do is a little bit of rearranging the things. That means C equals to GKCR minus GKCCH. So, that means C into 1 plus GKCH equals to GKCR. So, that means my output C over input R is nothing but GKC over 1 plus GKCH. That is what we have written here, KCS GS over 1 plus KCS GSHS. So, that is what will be the closed loop transfer function of this particular system. Now, with this model, we can have various types of KCS we can try. For example, we can try this type of a KCS, which is a PID KCS, which has some integrator, this is the integrator part of it, and then you can have a differentiator and the proportional part of it. So, again you can have something similar, but little bit simplified, k I as 0 you can have, and then you can have k C as this is known as PD controller. You can have a PI controller where k D will be 0, then this will be the form of it. So, you can try various types of KCSS as PID, PD and PI controller, and with that you can actually try here. There is a very simple system like a single degree of freedom system which is subjected to unit step input, and let us say that I know what is the stiffness, I know what is KD, I know what is KI in this particular case. In this case of course, this K is proportional part. So, this is Kp. So, I know Kp, Kd and Ki, that means I know the controller structure, and let us say the system parameters are m equals to 0.2 unit, C 0.001, K 0.5 and H equals to 1, assume a unity feedback system. So, with this system if I apply this particular controller, then what is going to happen? You will see that in the open loop such is the amplitude, huge amplitude, whereas the step signal that it is supposed to follow in the closed loop system. Once I close it, you can see that within about oscillation of about 2 cycles itself, within something like a 10-second, somewhere like this, you have already started to follow the unit step signal. So, that is the beauty of application of the active vibration control. This is where we are going to close today.